Can we go over the second one?
Yeah.
Also, do you use partial credit?
What was that?
Partial credit? I wasn't reading the word.
You know, I'm not sure. I don't grade them. So there's a guy named David that grades them. I think he awards partial credit. I'm almost certain it's not just right or wrong. Yeah. All right, number 2. Does anybody have an idea how to start? Yeah.
You have to choose. David. You have
Hey, did you guys have an idea how to start number 2?
I did, there's 13 values to
Right.
choose from, and there's 4 suits.
Right. So I like how you split the problem up into 2. Well, first of all, let's make sure we all remember what the problem is. It's how many ways are there to choose a full house, right? And her idea was to split the problem up into 2 sections, which was first, how many ways of choosing values are there, and how many ways are there to choose suits. And how did you go with the values? What was your idea? How many values there are to get a full house?
Oh, there's 13.
There's 13
different
values.
you can pick from.
Right. So how do you use that information?
It said 13 choose 4, but I don't know if that's
Okay. 13 choose 4. What are you choosing with the 4?
the suit, because we have to have 3
Okay.
other kinds, so there's going to be 1 from each suit,
So we want to put this over here under suits.
maybe.
Okay.
Yeah.
Okay. We'll come back to that in a minute. So what do you guys think about the values?
So I said it was like 13 times 4 choose 3.
13 times 4 choose 3 are the number of different values we can get. Why did you think that?
Because there's 4 parts for each value, and then you want 3 of them for the first part of the full house, and then there's 13 ways you can do that.
Right.
Or 13 values you can do that with.
Right. And then the next one, why did you get 4 choose 3?
Because you need to get 3 out of the 4 for the full house.
Okay, good. Is that the entire?
Well, no, you still need the other part.
Oh, the other part. Okay.
Yeah. But that's how I started it.
Okay. Right. And then so following in that pattern, how would we go then?
I think we would do, the next part would be times 4 choose 2,
Okay.
because you're choosing a pair out of the 4 suits.
Okay.
And then times 12, because you have to account for 1. I don't know how to explain that part in words, but I just know you minus it by 1. Can you explain it for me?
Because we picked a value for the first one, we picked like 3
Oh, yeah,
for the
yeah.
first one, there's only 12 values left.
Right.
That's what I was
Right. I agree. Okay. I think that is correct for the number of values. And then does everybody understand what I mean by values? You pick, regardless of the suit, you pick, okay, I'm going to have 4s full of 3s, as they say in poker. I'm going to have 10s full of 7s. Okay. And then in the suits, does anybody have an idea that Ken is eating 13 choose 4 is right? Or do we have another idea? Yeah.
For that one, do you multiply them together or do you add them separately?
Well, you mean for values?
Well, so the way I did it is like
Yes.
13 times 4 choose 3 plus 12 times 4 choose 2.
Okay, yeah, so let's consider that. 13 times 4 choose 3 plus 12 times 4 choose 2.
All of their 52 choose 5.
Oh, okay. So right away I can see that. Why did you divide by 52 choose 5 is a good question.
Because that's all the possible ways of choosing 5 cards out of 52.
Right, so I think you tried to solve a different problem than they asked. Because they asked how many ways are there to get a full house. And you were sort of going with, well, let me divide by the total number so I get the probability of getting a full house. Does everybody understand the distinction? Oh, maybe it was, and I'm reading it wrong. You're so right, you're absolutely right. Okay, I misread that.
We got it.
Because there was a homework problem about number of ways to get a full house. Okay, good. Okay, so at least this is the right general idea. You want to divide by the total number of ways to choose a card. So 52 choose 5, I agree, is the number of possible hands. And although I'm not sure about the addition, I don't think you would want to add here because here's why. For each choice of the 3 card, value. Like king, I have 3 kings. I can have 2 queens, 2 jacks, 2 tens, 2 nines, 2 eights, and these are all different possibilities. So you see why it's like multiplying, it's like a tree. Like for kings, you have 12 other possibilities. For queens, you have 12 other possibilities. You see how it's kind of spreading out? Okay, let's illustrate what I mean. So first step, choose the 3 card value. Now for each choice, possible choice. We can make, I want to say 12 choices of the 2 card value, and they're all different. Value, all different. So if I choose kings for the 3 card suit, then I have 12 options. Do you agree? Now if I choose queens, I have 12 options. So on and so forth. So do you see why that's multiplication, not addition? Okay, cool. Okay, so this is kind of a different route we're going with. So we definitely want multiplication here. And I wouldn't quite divide by 52 choose 5 yet, because we also want to account for how many suits there could be, right? So before we get to the division, which would be our last step, what was anybody's idea about how to count the number of possible suits? Do you want to multiply? Do you want to add? What do you want to add to or multiply by? Once I fix, like, so the idea is, first I fix the value. So let's say I'm going to have kings full of tens, which means I have 3 kings and 2 tens. How many possible ways of choosing the suits can there be? Did you have a thought, Alex?
For the denominator? I mean,
Oh, no, just I'm counting the total possible number of full houses. And then at the end, I'm going to just divide by all of the possible hands you can get.
So you want to define it divided by that number?
No, the top, we're still in the top. So first we
Okay.
counted how many values there could be, and now we're going to account for that, they could be different suits as well.
Isn't the fourth just accounting for the suits?
Yeah, that's
Yeah.
Yeah.
Yeah. Good point. Okay, 13, 4 choose 3, 12, 2. I agree, yep, that's the entire problem. Okay, now do the denominator. 52 choose 5. I think that's the right answer. Okay. Good. Somebody want to do another one? Another one? Okay. The last one. Okay. Toss a fair coin 3 times. Find the probability that at least 2 heads occurred, given that the second toss resulted in a heads. Jay, how did you go about this?
So the way I did it,
Yeah.
can you say the problem again? 'Cause I don't
Yeah,
have
so
it.
you toss a fair coin 3 times.
Okay.
What is the probability that at least 2 heads occurred, given that the second toss resulted in heads?
So what I did was, I made a sample space
Okay.
first and counted for 8 different possibilities or 8
Okay.
different combinations,
Okay.
which was, but we know that. And
Yeah,
then-
2 to the third.
Exactly, and then the event was, what was the given? What was the given?
Given that the second toss resulted in a heads.
Okay, so we're given that the second toss resulted in heads, so I
Right.
believe from what I got it was 4.
That cuts it down to 4.
Yeah, it cuts it down to 4.
Okay, so new sample space, and if this is, we'll call the new one A, as size 4.
Right,
Does everyone understand what I mean when I say the new sample space? Okay, good.
and then the question is asking, it's kind of like implying the intersection, even though it's giving you a possible B, but you lead to the intersection of 3 options that have 2 heads. So the second flip that has a head in the middle, you would choose 3 out of 4 of those options that would
Right.
intersect.
Right, I agree. So we have these 3 different coin flips. Here's 1, here's 2, here's 3. And now we fixed the second one to be heads. So that's written in stone now. So the question is, how many ways can we get 2 heads, and how many ways possible are there? Well, since this one's fixed, it's just like tossing 2 coins. You have 4 possible ways, 3 of them contain at least 1 head, and so that gets us a total of at least 2. So I think the answer is 3 out of 4. Did everybody get the same sort of idea?
Yeah.
Okay.
I did it a little bit differently to get 3 out of 4,
Okay.
but I mean, it's the same type of, like, there's a formula where you use like probability of B-A, which is event that B would happen if A happens.
Right.
And so I divided, I think, 4/8 or something, 3/8, 4/8, divided
Yeah.
by 4/8 or something, and
Yeah.
got 3/4. That's what
Right, right, so I know what you mean. So this is gonna lead into what we wanna talk about today, which is conditional probability. Now, I don't wanna go over just something that, why am I drawing a graph? I don't know. It's just instinct at this point. So I don't wanna just belabor something that Professor Penny's already covered, but, did he do this graph, I mean, this kind of diagram where he said like, here's the big sample space omega,
Yeah.
here's the thing that's gonna be given, and then we have the intersection here?
Yeah.
Okay, good. So are you guys clear on why probability of A given B is equal to the probability of A intersect B over the probability of B? Is that like crystal clear to you guys why that's the case? Just based
Why
on
do
the
you
picture?
have to divide it by probability of B?
Right, okay, yeah.
Is it A or B? Oh, you can
Divide
do
by
it two
B.
different ways, right? Can
Well-
you do
Yeah, you
B
can.
given A too?
Yeah, you
It's not the same thing, but yeah, you
Okay.
should do that as well. The other formula, here's formula 1. Formula 2 is the probability of A given B is the probability of B given A times the probability of A over the probability of B. You guys went over both of those? Okay. The second one's a little bit more complicated. The first one it should be really clear just from looking at the picture.
I feel like,
Yeah.
did you mean like if it's probability of B given A
Yeah.
instead of A given B?
Yeah.
You just flip the 2 letters in the beginning, so probability of B given A.
Oh, you want to do it the other way?
Yeah, then the denominator would be probability of A.
Sure. Yeah, so you're just making the point that B is, since B and A are just anything, you can just switch them around, right?
Yeah.
Okay. Yeah, I agree. Good. Okay. So does everyone see why that's the case based on this picture? You guys went over that, or you?
Why do you divide it?
Why do you divide it by B? That's the crucial point, is why divide by B? So I'm gonna erase this for a second because I don't wanna get confused between which one is given, okay? But suffice to say, we can always just switch them around, because it doesn't matter what they are. Why do you divide by B? Okay, so what does it mean to be given B? It means that we have some kind of information, and that's gonna influence the probabilities that we calculate. The information that we have is that B has occurred. So B is, let's review the kind of terminology. Is B an event or a subset? I was going to say, is it an event or an outcome? Sorry. Event, right? So B is a subset of omega. Okay? And now the information we have is that B has occurred. Right? So now all we're concerned with is what's within this circle, because nothing else is possible anymore. We already know that B has occurred. And now what's the probability of A happening? The old probability was the ratio of this circle to the whole thing, right? The new probability is, here's our whole thing, and now here's the part where A occurs. So it's probability of A intersect B over the probability of B, right?
Since they're both happening?
Here's the one where they're both happening, right?
Okay.
So the reason you divide by B, by probability of B, is that this is the new total number of things. Like this is the new possibilities, right? And what you want is the ratio of this, which is the part where A happens, to the whole thing. So I want to also call attention to the fact that like, if you just have a sample space, omega, you could still do this. It would be like what they call in mathematics trivial. The probability of A given omega, right, it's kind of a silly thing to see, but it works the exact same way, is the probability of A intersect omega over the probability of omega. So why is that kind of a silly thing to write? what probability of omega is 1, so it doesn't matter to divide by it. And the probability of A intersect omega is, what's A intersect omega? A,
Yeah,
right, because it's a subset of omega.
yeah.
Okay, so this is, you can go the same way, it's just a waste of time, because, right?
When you write B subset of omega, little like c, what does it mean when there's no line underneath it?
Oh, good question. So that's a difference in, it's like the difference between less than or equal or less than, right? But it's confusing because some people write this to mean that. So it's just a horrific mess. So if you have to really figure out what they're saying. If they write that B is a subset of omega without the line, it could mean that they're saying it's a subset and it's not equal to omega.
Okay,
So,
or,
I write it to mean subset or it could be omega, just to be clear. Some
is it the
people,
same thing, if I see it, I feel like I've seen it in the book,
with this or with just
with
that?
the C with no line underneath it.
Okay, yeah, I would just treat it like it could be omega. Yeah, most of the
So this
time.
means it could be inside omega or it could
Could
be
be the whole
all of
thing,
omega?
right? Because omega is a subset of omega too.
Okay.
It's just not a proper subset, as they say. It's not a strict subset. Okay, so everybody kind of understands this. Good. Yeah.
Could you do that problem with like actual mathematical formula? Because
Yes.
like the whole homework was like that, and I could only do it using logic. But then once the problems get more complicated, you have to use the formulas.
Sure. Yeah, that's a good suggestion. Okay, so everybody have this? Can I erase this? Okay. So, Mustafa, how would you start?
I have no idea.
Okay. Well, the way you always start if you want to go the subset route is you got to choose what sets you're talking about. So like, what are your events in this particular problem? What's given? What do you want to solve for?
So it's given that the second one's a heads, and
Given that, what? Second one is a heads.
Is a heads.
So what do you want to call that?
I guess A.
Okay.
Does it matter which one we call which?
No, certainly not. Letters are
Okay.
just letters. Yeah. Did you have a point?
Yeah, I have a different answer for that.
Oh, really? Okay. What was your
Because,
answer?
I said A is the event that the second clause is heads,
Yes.
and B is the event that at least two are heads.
Right.
So we are looking for A intersect B.
Well, you're looking. I would say, yeah. Okay. But you're looking for A given B is really what you're looking for.
Yeah, but
Okay.
A given B is
Yeah.
3/4. Because in the homework we were
Yes.
looking for A intersect B.
Oh.
So I said 3/4 times 1/2 because 1/2 is the probability of getting heads.
I know what she's saying, like in the
Oh.
book,
Yeah, because in
yes.
the book it was like that.
it specifies, like, we had to look it up ourselves, like, you know how P and then bracket B event of A is what we were looking for in this particular, like, you know how 3 or 4 is like,
P of B and then the vertical line then A.
yeah, like, that's what we were looking, like, we want in the case of the final answer, but the book went one step further and it was like looking for the intersection.
Yeah.
But then we assume like, okay, since we already have this problem at 3 or 4, why would we go further? So we looked in other sources and we found that the answer that we're looking for is the previous step to intersection. But you'll probably get the answer right because in order to get the intersection, you have to have that piece of the formula. So you did get the answer right, you just went a step further.
Okay. Well, so did you
So I
write?
just-
Yeah.
Yeah, I said like 3/4 times 1/2 because 1/2 was the probability of A.
Okay.
Yeah, and
I agree.
This was.
But what's 2/4?
What?
You said 2/4 times 1/2.
No, 3/4.
Oh, 3/4 times 1/2.
3/4 is B/A,
Yeah.
and times is A intersect B. 'Cause
Right.
I thought this question was asking that. But
Oh,
in the
okay.
book It was asking that.
What
Right?
did
Okay.
you get? What did you get for that?
3/8.
Yeah, that's intersect, yeah.
Yeah, that's the A intersect B.
Okay.
Okay, let's get back to this for a second. We wanted to do this the sort of the rigorous way, or I suppose like the subset method. And what did you get for the probability of A, Mustafa, or how would you go about calculating that? In fact, we just said it. So
Probability isn't that given, so is it just one?
no, just because it's given doesn't mean that it's one. In a way it does, but here's what I'm trying to say. The probability of A given B, the formula is the probability of A intersect B. Oh, I'm sorry, we want to do B given A because we switched them around. Okay, so you were wondering, isn't this just always 1 because we're given A? Right, was that your question?
Yeah.
Okay, well, no. The probability, this is gonna seem silly, but the probability of A given A is 1. But the probability of A given nothing is not necessarily 1. Right. Yeah, I would say it's a half, yeah. Okay, something over a half. Now what do we think about A intersect B? Well, first of all, what's B? What do we want to decide B is?
Getting at least 2 of them.
Right, okay. Okay. So what would you say the probability of that is, or is it easy to calculate or not really?
I guess it's easy for this one, but
Okay.
I don't know how to do it for.
Yeah, in general, it's hard, I agree. You can use, there are certain tools you can use to get the probability of A intersect B. One of them is, does anybody have an idea?
The tree,
What?
the tree.
A tree? Okay, that's a way of counting the different outcomes. I agree, that's a good way. This, you could do that in this case. You could make a little tree of the possible outcomes, but in the absence of that sort of information.
I kind of just made like anytime I look at the problem, I look at it in 2 parts and just kind of like, we had problems in the book that were like giving us 2 spades, right?
Yeah.
And then you have a 3rd spade. The intersection is all of them are spades, if you think about it that way.
Sure.
You know what I mean?
Sort of.
Like, it's kind of like, with these kind of problems when it's not easy, I imagine like an intersection of commonality, like
Yeah.
sometimes,
Right.
you know what I mean?
So you mean
like,
you just thought about what would the condition be for things to be
yeah,
intersect?
that's
Try to
basically
count.
what
Yeah.
that's basically what I was saying.
That's a good way.
You know what I mean?
So you're saying, yeah, we have enough information to count it as long as we know what A
Yeah.
intersect B really means.
'Cause,
Right, I agree. That's a good way. And then in some, there'll be a lot of situations you guys will come up with where you won't be able to just count it out like a tree. But did you guys get maybe a hint in class as to what the next sort of tool is to talk about intersection, probability of A intersection B? Okay, it starts with an I. Independence, right. Did you guys get to that? Okay, so
Yeah.
when 2 things are independent, probability of A intersect B is a lot easier to calculate. If you know if you know the probability of A and B, and it's just, what is it? The probability of A times the probability of B? Okay. So that will be another way you'll use to count that. But in this case, you don't need to go that route. You have something over a half. And this way you could just count it out, right? What's the probability, given the second one is the heads, what's the probability the other was 2? And I think the answer was what? 3 over 8, right? Does that answer your question? Okay, good.
Thank you.
Sure.
Could you just like show us how we would do one that we couldn't count out with the
Yeah.
independence?
Yeah, I will. Okay, so this is going to be kind of a silly example because I didn't get like a good example beforehand, but
There was one in the book where it was like, instead of 3 coins, it was 4, and then I didn't know how to do that one.
Oh, okay.
It was a lot harder to count out.
okay. There might be a shortcut for that one, we'll see. But so here's like kind of the most basic example where you would use independence. Okay, say you know that the probability of A is equal to, I don't know, a half. And you know that the probability of B is equal to a fourth. And you know that B and A are independent. Now, well, first of all, I'll ask what's probability of A intersect B? I mean, it's pretty simple, just plug in the numbers, right? So it's their product, and that is what? 1/8, right? Okay, so now you can calculate the probability of A, you can calculate the probability of A given B, and B given A, and so forth, right?
Oh, so they will like tell us when it's independent?
Yeah,
Oh, okay.
that's a good piece of information. Like you could, for instance, does anybody have like an intuitive of like what does independent mean? You know?
Can stand on water.
Right, they have nothing to do with each other in some way. I mean, that's kind of a first pass of an idea of what it means. They don't, one doesn't really affect the other. So, here's a good question. Suppose that A and B are independent events, right? what can you say about the probability of A given B? Have you guys done this? No? It's a good exercise in calculation, also in just kind of remembering what everything means. So suppose that A and B are independent. What is the probability of A given B? In terms of probability of A and B. Does anybody have a first guess, like what it would be? They don't depend on each other at all, right? Just the probability of A. Why did you say that?
Because if they don't have anything, if like if they don't affect each other, like probably with A, B and B, so it's
Right. So the fact that we know B occurred does not change our, it doesn't, as they would say in probability, it doesn't update our priors. In other words, that makes no difference as to the probability that we would calculate. And why is this? Like, let's make a little short mathematical proof of this. Let's just calculate it out.
Plug in the formula.
Right, plug in the formula P of A intersect B over P of B. And now what can you do with the top? PA over PB, right? Okay, so good. Did you guys do this in class? No?
Let's see.
Yes.
Yeah,
Okay.
we use it.
Okay, good. How much time do we have? 8 minutes? Okay. Does anybody have, I have something I'll talk about, but you guys can definitely ask a question if that's what you'd rather do. Is that the homework or about the test?
I have just like a concept question.
Sure.
If you're like taking out balls out of a bird, an urn, and you're replacing it, does that make it independent?
Yes. I would say that if you're using replacement, then the successive picks don't depend on each other at all. Yeah. Okay. Okay, so I just wanted to go over somebody brought up in my office hours that they were going to great labors to calculate binomial coefficients, which are now our good friends. And I was hoping to maybe save some people some effort. So how would I calculate 10 choose 2? I mean, obviously you could plug in the formula, but this really is one you could be able to do in your head because there's a really short way to do it. Some people probably know it. Right, 10 times 9 over 2 is what? 45. Okay, so how you just went 10 times 9 over 2 times 1, right? Does everybody do it that way?
Yeah.
Because I saw some people going, okay, no, 10 factorial over 2 factorial over 8 factorial, you know, and that's like way more work than you want to be doing, you know, because this obviously cancels all but the first 2 terms of the 10. You with me? So you just do, okay, now how about this? How about 10 choose 8? Same thing, why? Your complements, right? Does everybody know that 10 choose 8 equals 10 choose 2? And why that is? Okay, good. I just wanted to make sure that that was something we were all good on. So don't get bogged down in the calculations. Okay, da-da-da-da. Okay, I guess we have 5 more minutes. Do a quick problem. Anybody have a problem? Or I don't really have time to get into it very much, but anything from the book or? Yeah, sure.
So if you want to prove like A and B are independent.
Yeah.
So you want to calculate if A intersects B equals to A multiplied by 2B.
Yeah.
How do you calculate like A intersect?
Yeah, I mean, in general, it's hard, is the answer. It's not easy to calculate that sort of thing, and usually when you get a problem, it'll be in terms of, here's some piece of the pie, you gotta complete the rest of it, you know what I'm saying? So they'll give you enough to solve the problem. Okay.
Do you use like A given B?
That's something you could use, because you know how that relates to A intersect B over B. right? So it's like if you have 4 pieces of information that are floating around and you have 2 of them, you can use these various formulas to kind of get at numbers 3 and 4. Does that kind of make sense? Okay, so they're all related by these formulas, by the 2 formulas I wrote down earlier. So you should be able to solve, it's like solving for x in algebra problem. You have all the other stuff, yeah.
When he gave us the definition of independence to n events in class,
Yes,
he said must hold for all subsets of size k for all 2,
for all 2.
2 subset k subset n.
Okay, he's talking about
Why is
pairwise
it-
independence?
Yeah, why is it 2 because of every subset has an opposite subset?
No, okay,
Why is
so
it
I
2?
think what he's getting at, and I know we don't have that much time, but there are, in general, different ways of being independent when you have a lot of sets, right? So one of them is called pairwise independence, where that means that any 2 of them that you pick are independent, and we know what that means. Another way is that they're all independent at once, right? So those are different. And there's an example in the book that I saw that illustrates when one is true but not the other. Did you happen to come across
Yeah,
that?
so is the 2 just because it's pairwise, like because they're literally just 2 that you can pick? Is that where the 2 is coming from?
I would assume so. I
Okay.
didn't see that, but
I just didn't know, like, if he,
yeah, where's this 2?
yeah, if we ever had to like prove that or anything, or if it's just.
It's just a definition, right?
Okay.
Yeah, it just means
Okay.
like pairwise.
Okay, okay, thank you.
Oh, I'll have to give you out your inclusions from last time.
Alright.